Students, the next topic is the atoms and its sizes. Now we move on to this topic. Again, what I defined in the previous session, atom is nothing but a smallest or a tiniest or an indivisible particle of a substance, and that we call it as an atom. Now, when we come to the what about the sizes? What is the size of an atom for a given matter? It may be a solid, or it may be a liquid, or it may be a gaseous one. Before going to this one, what I have written here, just check it here. For 1 meter, we have 10 power 9 nanometer. This is, for example, 1 meter equals to 10 power minus 9 nanometer. Now look at here, I have written some different sizes of different atoms. Look at here, 10 power to the minus 10 is a size of an atom of a hydrogen, and here 10 power minus is a size of a molecule of a water, nothing but H2O. The last one is 10 to the power minus 8, that is a size of a molecule of a hemoglobin. I think you know that the hemoglobin is present in our blood. Now look at here, like that they are given different sizes for different atoms as well as the molecules, and this is how we are going to represent the size of an atom, and this is about the atoms and its sizes. The next one, after all these things, now look at here, and what about the symbols for a given matter, for a given element? How we are going to represent, how we are going to denote, how we are going to indicate. I have written some examples. Look at here, this circle indicates, and with a center point indicates a hydrogen atom. Then and this one again a circle with a shaded part, and this indicates the carbon. The next one simply a blank circle indicates the oxygen, and this is the phosphorus, and this one is the sulfur. Like that, in a modern days, now we are going to abbreviate the different elements by taking the different symbols. That's why I have written here modern day symbols. This is how we are going to represent an element or a different chemical substances. Now the one more, right now we are practicing the chemical names, the chemical symbols or chemical formulas with respect to, according to the organization. Look at here, this one, IUPAC. This is International Union of Pure and Applied Chemistry, an organization called International Union of Pure and Applied Chemistry. According to the IUPAC suggestions, according to this one, we are going to follow the symbols, we are going to follow the chemical names, and etc. Now, before the arrival or before this IUPAC, the different elements or different chemical substances are originated by the Greek word, by the Latin word, by the German word, or by its native place. What is that native place again? Where these elements are going to found abundantly, then we are going to use by the places where they found, we are going to use those names. For example, I have written the very first one, copper, and this is a Cu. This indicates element called copper. This copper, how we are going to abbreviate this copper? This copper is hugely abundantly found in a place called Cyprus. There, by using that Cyprus word, we are going to use a word called copper. Then again I have written some symbols here. This indicates Cl, chlorine, and this Zn, zinc, and this Fe indicates the iron, and this K indicates the potassium, and this Na indicates the sodium. Now you just look at these symbols. I have written everywhere here, the very first letter is a capital one, and the next one is a, what is that, a lowercase one. Then this one, the very first one indicates the capital word or a capital letter, and this is an uppercase letter, and the very next one is a small letter or a lowercase letter. Okay, why we are going to follow this one? These type of recommendations are given by the IUPAC. Okay, and what about this? Again, I will take some example like this: chlorine and the zinc. Chlorine, okay, Cl, I have taken the Cl, and zinc, I have taken the Zn. And for example, some kind of elements like chlorine and zinc, we are going to use the first letter and the second letter of that particular word. Chlorine, Cl, zinc, Zn, like that. Okay, then this iron and potassium and sodium. For example, you take the K, that indicates the potassium, and this potassium is originated by a word called kalium, and this Na indicates the sodium. This is originated from the natrium. Like that, we have different elements. We have different symbols. Okay. The fundamental concept is that how we are going to write that particular chemical symbol. For example, the Cu, Cl, Zn, Fe, you take any element, we are going to write the very first letter is a capital 1 or uppercase 1, and the next one is a lowercase 1. That is how we are going to write the chemical symbols as well as these denotions, or for example, these abbreviations. Okay. Then after that, we have one more, atomic mass. And you know that you might be very familiar with atomic number, atomic mass number, okay, and all those things. And the atomic mass. Then when we come to the definition of the atomic mass, the total number of protons and the neutrons present in a nucleus of an atom. But what I have written here, some kind of a different example. Then atomic mass. For example, I have written, look at here, CO. This is carbon monoxide. Why that is a monoxide? Because a single oxygen molecule, right? Then CO. To produce CO, 4 gram of oxygen is required and 3 grams of carbon is required. This is experimentally proved one. For that reason, I have written here. This is experimentally proved that 4 gram of oxygen and 3 grams of carbon required to form a carbon monoxide. Then what it indicates, what it shows, nothing but the carbon combines with 4/3 of the oxygen to produce this carbon monoxide, this 1 gram of a carbon monoxide. For that reason, it requires 4 gram of oxygen and the 3 grams of the carbon. Then this we call it as AMU, atomic mass unit. To produce one mass unit or to produce one atomic mass unit of this carbon monoxide, it requires 4/3 of the carbon. 4/3 of the carbon. This is the atomic mass unit, and they have followed so far. Then nowadays they are going to use a symbol called a small u, and that indicates unified mass. What is this unified mass? For example, you take some assumptions like I have written here to produce any kind of a chemical substance, to produce any kind of element or a compound, you take anything, it requires 1/16th of the naturally oxygen atomic mass unit. To produce any chemical substance, any chemical substance, it requires 1/16th of the naturally occurring oxygen by mass. Why we are taking this oxygen only? Because in nature we have so many elements, we have so many compounds. To form compounds, there should be a reaction between the two elements. Then as much as possible, many number of compounds are formed with the reaction of the oxygen only. You take any compound, there should be a reaction between that particular element with the oxygen. For that reason, we are considering the oxygen. Then afterwards, the combination of any two elements results in a compound. The atomic mass unit is very nearer to the whole number of this 1 over 16. I think you know that the whole number, for example, you may get some value that is very near to this one, 1 over 16. For that reason, they practiced so far this with respect to the oxygen. For that reason, you have to write like this 1 over 16. But nowadays, according to the recommendations or suggestions given by the IUPAC, they are following, they are considering, and that is moreover universally accepted that 1 atomic mass unit is equals to 1 over 12 or 1 by 12 mass unit of the carbon. And you know that the atomic number of a carbon and the mass number is 12. To form any compound, for example, any atomic mass unit of any element or a compound, that atomic mass unit should be equal to the 1 over 12th of the carbon atom. This is nowadays they are following, and moreover this is universally accepted, that one. Okay, and this is about your atomic mass and its atomic mass units. Thank you.